Welcome to today's paper reading. Today's paper is titled Correspondences of the Third Kind, Camera Pose Estimation from Object Reflection. This paper was published on AR14 by Kohei Yamashita and colleagues from Kyoto University. In this paper, the authors introduce a novel concept called reflection correspondences, which represent a third kind of correspondence in computer vision. These correspondences are point correspondences in the reflected world, meaning the scene is seen through the reflection on an object's surface. The object's geometry and reflectance properties alter the scene both geometrically and radiometrically, which can lead to incorrect pixel correspondences. Additionally, the geometry recovered from each image is often hampered by distortions such as the generalized bas-relief ambiguity, resulting in erroneous 3D correspondences. The authors demonstrate that reflection correspondences can effectively resolve these ambiguities. They propose a neural correspondence estimator and a ransack algorithm that fully utilize all three kinds of correspondences to achieve robust and accurate joint camera pose and object shape estimation solely from the object's appearance. This method has significant implications for various downstream tasks, including camera pose estimation for appearance modeling and motion estimation of reflective objects, as it eliminates the need for overlapping background information. In the introduction, the authors contrast human intuition with computer-based methods in estimating camera pose changes. Humans can understand camera movement even with perfect mirror objects due to our ability to separate reflected surroundings from surface appearance. In contrast, computers struggle because traditional structure from motion methods rely on pixel correspondences, which fail due to the color constancy constraint violation by glossy reflections. The authors highlight the generalized bas-relief ambiguity, where illumination and surface geometry can create the same object appearance, leading to distorted space pose estimation and potential local minima in geometry estimates. To address these challenges, the authors propose using reflection correspondences, which involve leveraging single-view reconstruction to extract reflectance maps and resolve the bas-relief ambiguity, thereby enabling accurate camera pose estimation from object appearance alone. Figure 1 illustrates the challenge of camera pose estimation between two images for both humans and computers. Humans can qualitatively understand the camera movement due to their ability to separate the reflected environment from the surface appearance. However, computers struggle with this task because traditional methods like structure from motion rely on pixel correspondences, which are unreliable due to the glossy reflections violating color constancy. The introduction of reflection correspondences aims to resolve these issues by establishing correspondences in the reflected world, thereby addressing the generalized bas-relief ambiguity and enabling accurate camera pose estimation from object appearance alone. The estimation of camera pose for textureless, non-Lambertian objects presents significant challenges. For textureless objects, establishing correspondences is difficult due to the lack of distinctive features. Texture-based correspondences are often sparse, necessitating a large number of images with significant visual overlap for accurate estimation. Non-Lambertian objects, particularly shiny ones, pose additional difficulties as good initial estimates are required to avoid local minima in joint optimization processes. In contrast, reflection correspondences offer a solution by enabling the recovery of camera pose and object geometry under complex natural illumination without the need for a static overlapping background. Figure 2 illustrates the utilization of three distinct types of correspondences for camera pose estimation. The first type, pixel correspondences, A, involves matching pixels that represent the same surface point across two images. The second type, 3D correspondences, B, involves matching surface normals in the two images, which is useful if the normals at the matched image locations are known. The third and novel type, reflection correspondences, C, involves matching image locations where light rays reflected by the object surface come from the same direction in the two images. These correspondences are detected from camera view reflectance maps, which are view-dependent maps about the surrounding environment. This approach allows for the estimation of relative camera poses from object appearance, even in the absence of texture and with strong specularity. In this section, we discuss the three types of correspondences used for camera pose estimation. First, pixel correspondences link corresponding locations in two images, providing a constraint on the camera rotation under orthographic projection. Second, 3D correspondences relate to the normals at matched image locations, but are subject to the generalized bas-relief ambiguity. Finally, reflection correspondences match image locations where light rays are reflected from the same direction, providing additional constraints on the relative rotation. These correspondences, when combined, allow for the estimation of the camera pose, despite the challenges posed by the ambiguities. Figure 3 illustrates the challenges in camera pose estimation, particularly under orthographic projection. The generalized bas-relief ambiguity in single-view surface normal recovery and the fundamental difficulty in structure from motion prevent obtaining a unique solution for the relative rotation from pixel and 3D correspondences. However, reflection correspondences, which relate to the incident directions for specular reflections, provide a means to distinguish the correct relative rotation from other possible solutions. Figure 4 illustrates the process of estimating the relative camera pose from two-view images of a textureless, non-Lambertian object. Initially, the surface normals and reflectance maps for each view are recovered using a single-view geometry reconstruction method. Subsequently, a novel deep feature extraction network is employed to establish 3D and reflection correspondences, which are then utilized to compute the relative camera pose. This approach ensures accurate pose estimation by leveraging detailed geometric and reflectance information from the object's surface. Table 1 presents the accuracy of camera pose estimation, specifically the relative rotation, across different datasets and methods. Part A shows the mean accuracy on synthetic images from the NLM-VSynth dataset, where our method achieves a pose error of 4.5 degrees. Part B compares the accuracy on real-world images, with our method achieving a significantly lower error of 1.9 degrees compared to other methods like CalMap, which has an error of 15.7 degrees. These results highlight the effectiveness of our approach in accurately estimating camera poses from both synthetic and real-world images. In the evaluation of synthetic data, the method was tested on 27 combinations of shapes, BRDFs, and illumination environments. The accuracy was measured by the geodesic distance between the estimated and ground truth relative rotations. Comparisons were made with ablated variants to highlight the importance of joint estimation, data augmentation, and reflection correspondences. For robustness to flatness, the method was tested on shapes with varying levels of flatness using GBR transformations. The results showed that the proposed method is robust across different flatness levels, unlike the baseline method. On real data, the method was applied to real objects without fine-tuning and compared with CalMap, Light Glue, and Samurai. The proposed method successfully recovered plausible camera poses and surface geometry, demonstrating its effectiveness in real-world scenarios. Figure 5 evaluates the method on synthetic shapes with varying levels of flatness. Part A illustrates the creation of these shapes using GBR transformations with different lambda values. Part B presents the accuracy of pose error for each lambda, demonstrating the effectiveness of using reflection correspondences. This evaluation highlights the robustness of the method across different flatness levels, as detailed in the accompanying text. Figure 6 illustrates the reflectance maps, RMs, normal maps, surface geometry, and relative camera poses that have been recovered from two-view real-world images. This figure showcases the effectiveness of the method in accurately estimating these parameters from real-world data, which is crucial for applications in computer vision and 3D reconstruction. The reflectance maps provide information about how light interacts with the surface, while the normal maps detail the surface orientation. The surface geometry gives a comprehensive view of the object's shape, and the relative camera poses help in understanding the spatial relationship between the two views. Together, these elements form a robust framework for camera pose estimation and object reconstruction from real-world images. Figure 7 illustrates the various types of correspondences identified from the real image pair presented in Figure 6. These correspondences include reflectance maps, RMs, normal maps, surface geometry, and relative camera poses. The detection of these correspondences is crucial for understanding the spatial relationships and characteristics of the objects within the images. This figure provides a comprehensive view of the data extracted from the image pair, highlighting the detailed analysis conducted on the real-world images. Figure 8 presents the results of our camera pose estimation method compared to a baseline structure from motion (SFM) method on scenes containing both textured and textureless, non-Lambertian objects. Despite the cameras being almost orthographic, our method, represented in green, accurately estimates the relative rotation, closely matching the ground truth in blue. In contrast, the SFM method, shown in orange, struggles to recover the angle between the two views. This highlights the effectiveness of our approach in handling complex scenes with diverse object types. For more detailed results, please refer to the supplementary material. In this study, the authors introduced a new type of correspondences called reflection correspondences. These correspondences enable accurate and robust camera pose and joint shape estimation from the appearance of textureless, reflective objects. This innovation not only eliminates restrictive requirements for image capture and camera pose estimation but also opens up new applications for object appearance. The authors plan to explore these applications further in future work and aim to catalyze research in this area by releasing their code and data. The research was supported by various grants including JSPS Kohei, JST, Reich and GRP, ANR Project OSI, and the ERC Grant Explorer. Thank you for watching.